Stop memorizing. Learn visually. Balaji Crafts and Tutorials. Master Math, Science, and Kannada. Visit our website and subscribe.
We don't actually see objects. We only see electromagnetic energy hitting obstacles. This is a technical breakdown of the specific behaviors light exhibits when it interacts with the physical world. Human vision depends entirely on reflection. Objects do not inherently broadcast details to our eyes. Rather, they serve as solid obstacles. When light waves from a primary source hit an item, the light bounces away and travels directly into our retinas. Without this specific interaction, our surrounding environment remains in complete darkness. Reflected light rays alter spatial depth to produce two distinct categories of images. A real image forms when light rays physically meet at a specific focal point after reflection. Because these rays actually intersect, a real image can be projected onto a solid wall or screen, similar to how a theater projector throws moving pictures onto a cinema screen. Conversely, a virtual image forms when light rays diverge and never actually cross. They only appear to meet when projected backward behind a reflective surface. Everyday bathroom mirrors generate virtual images that cannot be captured on an external canvas. These flat surfaces produce a mechanical flip called lateral inversion. While the visual structure remains upright and scaled at a perfect 1-to-1 ratio, the horizontal orientation reverses. This is why when you lift your right hand before a mirror, the reflection lifts its left. This behavior explains why emergency response units paint the text ambulance backward on vehicle hoods. When drivers look into their rearview mirrors, lateral inversion corrects the reversed lettering so it displays forward. This brings us to the first CBSE exam marker. Reflection is the systematic bouncing of light rays. Distinguishing between a real image that can be projected and a virtual image that cannot is the first step in analyzing any optical system. Light follows strict geometric rules upon impact. These mathematical constraints apply to every interaction between a light beam and a boundary surface. We define this geometry using 3 lines: an incoming incident ray, an outward-bound reflected ray, and a perpendicular axis forming the normal line. Law 1 states the angle of incidence always equals the angle of reflection. Additionally, the incident ray, reflected ray, and normal all sit flat within the exact same plane. When parallel rays hit a uniform, polished surface, they depart perfectly parallel. This is regular reflection. However, if those same rays hit an uneven surface, like crumpled foil, the light hits microscopic bumps sloped at random angles. The rays scatter in multiple directions, resulting in diffused reflection. For the second CBSE exam marker, chaotic scattering does not mean the physics changed. If you examine an isolated microscopic hill on wrinkled foil, the angle of incidence still equals the angle of reflection. The scattered appearance is a consequence of Sousa's texture, not a breakdown of geometric laws. By positioning mirrors together, we create a continuous feedback loop. An image produced by the primary mirror acts as a physical object for the adjacent mirror, creating multiple reflections. A kaleidoscope uses this behavior by arranging 3 mirror strips at 60-degree angles. As the tube rotates, gravity shifts colored beads inside. The mirrors multiply these random shifts across multiple axes, forming symmetrical patterns that never repeat. We can further manipulate these images by changing the shape of the reflective surface. Spherical mirrors, which are shaped like part of a hollow sphere, alter the image size and orientation based on their curvature. A concave mirror curves inward, acting as a converging tool. When an object sits close to it, the mirror creates a magnified, upright virtual image, the exact effect needed for dental tools or shaving mirrors. However, moving the object further away forces the rays to cross early, flipping the image upside down. A convex mirror bulges outward and scatters parallel light rays away from each other. These diverging mirrors always produce smaller, upright virtual images. This reduction in size allows for a much wider field of view, which is why they are installed as vehicle side view mirrors and safety mirrors at blind turns. This is the third CBSE exam marker. By choosing to converge light with a concave curve or diverge it with a convex one, we can build specialized tools for either high magnification or wide area surveillance. We also control light by passing it through transparent objects. Instead of bouncing light via reflection, lenses bend light via refraction. A convex lens is thick across its center and tapers at the edges. It bends light inward toward a shared focal point. This convergence allows it to function as a magnifying glass, enlarging the appearance of objects held close to it. A concave lens is thin across its center and thick at the edges. It bends light outward, spreading the rays apart. This divergence always results in an image that is upright and smaller than the original object. The fourth CBSE exam marker covers a frequent technical trap. Lens behavior is the inverse of mirror behavior. Convex lenses converge light, while convex mirrors diverge it. Concave lenses diverge light, while concave mirrors converge it. The human eye is a biological camera. Light rays first pass through the cornea, a transparent protective shield, before being focused by a biological lens. This lens projects the incoming light onto the retina, a nerve-packed screen at the back of the eye. Vision defects like myopia or nearsightedness occur when this system fails to focus light correctly. In these cases, the biological lens converges the rays too early, causing the image to form in front of the retina rather than directly on it. We correct these biological errors using the physics of refraction. By placing a manufactured lens with a specific curvature in front of the eye, we physically adjust the light's trajectory so it hits the retina precisely. This is the final CBSE exam marker. Understanding light provides the technical basis for every optical instrument we use, from the lenses in a pair of eyeglasses to the biological mechanics of the human eye itself.